Okay, so here we're looking at the velocity time graphs now. They look pretty similar to the distance times graphs, so just be careful to really read your axes and read the question and make sure you know what you're on about. So I'm just going to draw out a velocity time graph. Okay, so you've got time along the bottom axis on the x-axis and the velocity in the y-axis. And again, there's some points to remember and key points on how to read the graph. So the first one is that the gradient in this case is the acceleration. So this is, the acceleration is how fast the speed is changing. Okay, so whereas in the distance time graph the gradient equals the speed, in a velocity time graph the gradient equals the acceleration. That's really important to remember that difference. A negative gradient here equals deceleration, so a speed that is getting slower. Flat sections in this graph show a steady velocity, so no change of speed, and whatever's travelling is travelling at the same speed and the same velocity. And finally, and this is very important to a velocity time graph, is that the area equals the distance. Okay, so those are 4 points to remember. So if we look over here at the velocity time graph, we can see that at the start, whatever has been moving is increasing in velocity, so it's accelerating. So we're accelerating here. Say this is a car, the car's accelerating, then at the flat area here, it stops accelerating and just maintains a steady velocity, so it starts going at the same speed. Then it accelerates again to an even greater speed, and then here it decelerates, so the speed of the car gets slower. And the area under here, so all this area, equals the total distance travelled. Okay, so now I'm going to show you an example. Okay, so a sprinter runs a race of 200 metres. Her total time for running is 25 seconds. And here's the velocity time graph to show that. Calculate A, the acceleration in the first 4 seconds, B, the distance covered in the first 20 seconds, and C, a value for U. So if we just look at the graph first to see what's going on, we've got the sprinter starts. She accelerates, then maintains a steady speed to 20 seconds and then decelerates just before the end. Okay, so if we're looking for the acceleration in the first 4 seconds, we just want the gradient, because the gradient is the acceleration in the first 4 seconds. So the gradient is 9 divided by 4, which equals 2.25 metres per second squared, because we've divided a metres per second by a second. So yeah, it's important to remember the units. Actually, I might just write them down here, just so you remember. Okay, so B, the distance covered in the first 20 seconds. So the distance is the area under the graph, so we want the area under the graph in the first 20 seconds, so that's up to this point here. So the easiest thing to do here is just to split it into 2 sections. So we want the area of this triangle added to the area of this rectangle. So remember here, the bottom of this isn't 20, it's 20 minus 4, which is 16. Okay, so that's question B. Now the hardest point on this question is C, finding a value for U. And we have to go right back to the start and remember that the total distance of the race is 200 metres. I'll kind of just cross that out. Whoops. We know the total area under here is 200 metres, and we've just worked out here the area of under the graph up to 20 seconds. So to find out U, we're going to find the area of this final trapezium. So if you just follow this step by step now. So the area of the trapezium is going to be the total area, which is 200, minus this area here, the area under 20 seconds. So that's going to equal 38 metres. So if I use colour, it might be easier to see. So it means this area there, shaded in purple, is 38 metres. And so we know that the distance is 38 metres, and the area, because the area under the graph is the distance. So the area of the trapezium is 38 metres, and the area of a trapezium equals half times these two sides added together, so that's going to be 9, which is the length here, plus u. That's going to be times by the width, which is 5. So now we just have to rearrange this to find u. So I'm first going to times this side by 2, and then divide by 5, 15.2. So that equals 9 plus u, and then I just take away 9 from this side, and u equals 6.2. And remember the units because it's a speed, so 6.2 metres per second. Excellent, so that's a run through of that example. Yeah, basically just try and remember how to read the graphs really, and what it means when they're flat, what it means, what the gradient means, both in the distance time graphs and the velocity time graphs, and you should be able to answer all the questions. One quick thing to go through is estimating gradients and areas if you're given a graph that's not dead straight lines, so I'll just go through that quickly to finish this video. Okay, so here you've got some more realistic graphs, so they're not dead straight lines, they're actually a curve. But if you got given this graph here, so this is a velocity time graph, and you were told to estimate the distance, the total distance travelled, so that's the distance under the whole graph, how would you go about that? Well, you'd actually just estimate it as straight lines. So you can see here that I've just turned these into trapeziums so that they're easier to calculate, and it will underestimate the distance slightly because most of the red lines fall above it, but as an estimate that's absolutely fine. So you just find the area of the different segments individually and add them all up, and that's how you would estimate that. So in the second example, how would you estimate the gradient? Well, you could be asked to estimate the gradient between two time points, so say between the time here and the time here, and in that case you just draw a straight line connecting them and work out the gradient of that line. Or you could be asked to find the gradient of a point or at a certain time, so you might have to find the acceleration at that exact time. So you just draw a tangent, so a line that just touches it in one point, and you'd work out the gradient of that tangent. Yeah, there you go. That's how you would estimate if they were curved and more realistic velocity time graphs.